This conference will now be recorded.
Good morning and welcome again to the Mirabilis Design Technical Webinar Series. Today's topic is Unlocking the Power of Performance Modeling. I'm your host, Deepak Shankar, and I will be walking you through the next 45 minutes or so on an explanation on performance modeling and how it can help your product development. We'll start off with some brief encounter about performance modeling and then move to some examples, real-time examples that you can use to visualize how you can utilize performance modeling. Before we get started, there's some logistics. Right now, everybody's set on mute, and we'd like everybody to stay on mute till the end of the presentation. The session is being recorded. We'll provide you a link to the recording at the end of the session. The panel on the right-hand side of your window will have a chat section where you can type in your questions, and there are people that will be ready to answer them for you. And also, I plan to keep a watch on the questions so that I can answer those questions as and when the appropriate section of the presentation comes along. With this, I would like to get started on the session. A quick introduction to Mirabilis Design before we get going. We're a company that provides architecture exploration software. We've been in the business for about 15 years now and have over 60 customers. The name of our product is Visual Sim Architect, and the key innovation that we provide is a large number of system modeling IP that allows you to quickly assemble up your systems. The goal of Mirabilis Design's products, Visual Sim and our libraries and our analysis tools is to enable you to select the right configuration to match your requirements. A quick look into the agenda. We're going to walk you through the role and challenges and the types of performance modeling, and then we will demonstrate performance modeling application in about 3 or 4 different market segments. Before we get started, just want to talk a little bit about where does the performance modeling fit in the product development process. The whole goal of performance modeling is to test it before building it. You want to be able to understand what your system is going to be doing once you go into integration. So you want to eliminate all the surprises before you get to integration. The way you do it is by experimenting with different user scenarios, traffic inputs, different types of configurations, so that you can optimize your specification before you actually start doing development. This might involve identifying all the bottlenecks, looking at resource efficiency, looking at power consumption, looking at the usage of different resources, can be buses, memories, DMAs, peripherals, the processing core, and so on. Let's look now at the why performance modeling is a requirement. There's a number of different scenarios that really cause it to be critical in the early design process. First and foremost is the fact that different parts of design are typically designed at the architecture phase or systems engineering phase by different entities, either different groups, different companies, or even different people within the same organization. Now, many times these are not brought together until much later in the design process. As a result of that, you see that the development is kind of distorted or disjointed in its approach. So as a result of which you create a design specification that does not take into requirements of all the different pieces, might take in 1 or 2 or a few of the total number of designs. So one of the areas where performance modeling helps is in bringing everybody together, putting the whole system design in a single perspective. The second area of system design is really looking at concurrent software execution. One of the things that you look in a lot of today's systems is you have a single application processor or a single infrastructure bus or a memory infrastructure that caters to a number of different resources. When these resources all start behaving or interacting with the system, you will notice that there is multiple use of different parts of the design. So for example, here, even though I've got three distinct components that are being executed associated with each one of these tasks of a single application, I see some overlaps right here on the buses and on the bridges. Now, not so much of an issue when there's only one task at a time that's executing. But when, say, you have the first packet being executed here and the fourth packet being executed here, you can start seeing that there is some conditions where there is some overlap that's occurring on these resources. Now, these become a little more acute when you start incorporating multiple applications with each with their own set of tasks and each of their tasks executing differently. So in these cases, the scheduling and the arbitration becomes a key element or a key challenge that you have to address. Now, this is where you can look at all these architectures, these different variations, and realize that there could be unexpected or unpredicted performance. So for example, in this particular design that we were looking at, what you'd end up finding is we tried two different scenarios. One is running a 200 megahertz bus, and the other running a 400 megahertz bus. And you'll see here that the 200 megahertz bus as a whole runs, takes more time to complete these list of tasks, these two sets of applications. It takes a little more time to complete them. Now, there are scenarios where the 400 megahertz task actually takes more time than the 200 megahertz task. Now, you can look at it and say that at those locations, something wrong is happening. So you want to look at exactly what was the error in those locations. Or you can take it one step further and assume that this was actually a build-up. So it wasn't really happening just at that instance, but there are things happening earlier than that. So for example, you can see here that I already had a spike here, and then I got this big spike. While on the 200 megahertz, I got the spike, but it didn't spike up as much as for 400 megahertz did. Similarly, you can see that this one here, the spike occurred a little bit earlier than this one. So allows you to evaluate, was it a buffer problem? Was it that too many tasks were hitting the processing unit or the memory at the same time? So allows you to figure out what is the range of operation, meaning what is your range of latencies, range of throughput, range of utilization of your system. Another aspect, and this is probably the most important reason for system modeling, is really meeting the timing requirements. Now, the hardware architecture, the platform architecture is really constrained on providing the requirement or the resources required to execute your application. Application can be software or a combination of software and FPGA or a combination of software and IP blocks within your application processor. Now, one of the things you would expect here is that, I've got the software that started here. Software that started here, and I expect it to complete by this point. But in reality, the software started here, really completed here. So it took 300 seconds or 300 units of time longer than it was expected to complete it. So you would assume that somewhere over here, there was a bottleneck. But in reality, this particular software was getting preempted multiple times. Matter of fact, got preempted 3 times before it completed its task. The reason being is 2 higher priority tasks came along. So one of the things to consider is if this was a high priority, say a diagnostic on an automotive, or maybe a connection for for like a constant data rate element, you may want to figure out how to provide this a high priority or provide it a dedicated bandwidth on a virtual channel or things like that. So with this type of a flow diagram or a timing diagram, you can visualize, conceptualize what is happening prior to the system executing, that is causing this delay. So allows you to visualize the problem and also realize how you can arrive at a solution. So timing requirement is probably the #1 reason, apart from the other 4 items we discussed, that allows you to utilize performance modeling or take advantage of performance modeling. Now, there are really 5 different types of exploration around performance modeling. First and foremost is performance analysis. So these relate to statistical and workload studies. So for example, if I increase the traffic on say a bus architecture, so like a network on chip or say a token ring, what is the latency as I go from say 1.6 gigahertz at in a 64-byte request to like say 4 gigahertz at 16-byte request? What is the impact on the system? The other aspect is looking at it at a very detailed level where I'm sending these requests to a specific address in memory or a specific peripheral across this bus. What is the response time? Say, for example, I keep sending it sequentially to the same memory address, or I vary it where I send it to one memory controller, later send it to another memory controller versus sending it to another processor with its own memory. Looking at a signal and at a message and also at an address level. The third aspect, which we're not going to go into detail today, but how does power consumption or energy consumption play a role relative to making decisions around your performance? So, for example, if I incorporate, say, a power management based on a state-based architecture, how does that impact the response time, or how does that impact my ability to complete a certain job within a time constraint? The other aspect is, now that we looked at the performance, which is more the timing and the power impact on it, the next one is looking at the functional impact on performance. So these, where you can look at, for example, I change the arbiter, or I change the weightage for different resources and I do a round robin, or I change the behavior task graph to modify it to be one flow versus another flow. How does the system impact? Another aspect is looking at hardware-software partitioning. So how do I do a trade-off based on, say, I move some of the tasks, say I start with F1, F2, and F3, and can I move F2 over to an IP block or to an FPGA? How does the end-to-end response time behave? So at this point, I'm just going to go over to show you a quick demonstration of how something like this can be built up. So what you're looking at is the Visual Sim modeling environment. This is our graphical modeling environment with a series of building blocks on the left-hand side. What I can do is I can open this, say, file new. I can link it up to, say, open a simulator and say I'm going to run this for about 10 units of time. And then I can drag and drop a traffic generator. And just to see what it looks like, I'm going to set this up, connect this thing together, set the number of events we want, and run it. So what this does is, based on a discrete event simulator, it generates a series of transactions. A transaction is another name for a struct in C or C++, has a series of fields and some values associated with the fields. Now, how can I use this? 2 things. One is, there is a traffic generator that's generating based on certain time schedules, so it can be based on a distribution, a sequence, a trace file, any of those kind of attributes. Another thing that I can do is I can modify the behavior based on some of the fields of that data structure. So what I can do here is I can bring another block in here. I can connect this up, and for now I can just leave it. And then what I can do is add a resource to the same system. So we'll add a resource that resembles a bus, for example. So what I have over here is, and I'm just going to say, I'm not going to worry about anything. I'll just say, I'm going to run this. Every request that comes through takes 1 second to go across this bus. Connect them up. I'm going to go ahead and rerun it. Now what you're going to notice is earlier on this came in at 0. It took 1 second, 2, 3, 4. I can change this to say 1.5. Rerun it, and you'll see how this changes. Now, next, what I can do is I can, consider that, I want to randomize this response time across the bus. So I say that, I want to randomize it between, say, 0.8 and 1.6. I'm going to go ahead and say, rather than just putting a delay, I'm going to say, actually look up that value. I'm going to go ahead and run this. Now what you're going to see different is, I noticed that these are actually arriving at different times. Now what I want to do next is actually see what are the statistics associated with this one. So I'm going to go here and I'm going to take this. I'm going to call this the bus. Take this one over here. This over here. Connect this one over here. I'm going to go ahead and run the simulation. So what I noticed at the end of the simulation is that you can see the number entered with 10 because I was sending it every 1 second. I was running it for 10 seconds. But notice only 7 of them got out. So I got a max buffer occupancy of 3 with an average of about 1.8. And you can see even though I set the delay to be a max of 1.6, I see the worst case to be 2.755. And this is what is telling me that, I've got excessive delay across the structure, especially because I see my utilization to be 99%. So this, in a sense, is where you have a randomization of your traffic. So you're trying different traffic scenarios, randomization of your processing, and then looking at the statistics associated with this particular architecture. Now, I'm going to move on to something that I've already pre-built, which is the architecture you just saw a little while ago, where we had 2 buses, a bridge, 2 processing cores, a DSP, and an I/O interface. I've got 2 applications running on these. These are my software task description, and they get a mapping of each one of these onto one of these different resources. Now, what I'm going to do is I'm going to go ahead and run it, and we're going to make a special attention to this one over here, which is the time it takes for this application 2 to complete. So you can see it went from about 1.0, so it's about 1.0 microseconds, goes up to 1.55 microseconds. Now I can look at the statistics on some of these. So like the DSP took 48%, the IO was 81%, the bridge was 49%, and bus 2 was 31, bus 1 is 30, and the CPUs was, the second one is 55%, the first one is 92%. Now what I'm going to do is I'm going to slow it down, the buses, take both of these buses and make them 200 megahertz. Same model, so we got between 1 microsecond and 1.55 microseconds. Same design, but we went from like about 400 megahertz bus to a 200 megahertz bus, so almost half. I noticed here my latency did not start at 1 microsecond, but started at 1.32 microseconds. But earlier on, we were at 1.55. Now we're at 1.54. So the 200 megahertz actually narrows down the range of latency as opposed to the 400 megahertz, where it's much wider. Now, I can start reviewing it in different views. So for example, here, I'm looking at the time it takes to process, which is essentially on the pipeline, versus the transfer time it takes to go across the buses to the different CPUs or the different memories, and try to figure out where my latency or bottleneck is. Also, I can use this to look at them to see if there's any of them that are over-designed. So you can see DSP didn't have much change, the IO did not, the bridge did not. The bus 2 did go from 31% to 62%, so it doubled. This one also went up, bus 1 also went up. The CPU2 went up a little bit. CPU1 didn't really have much of an impact. So you can see that really what was happening was the bus usage went up, didn't double, went up, but then that caused a huge change in the performance of my latency, or huge impact on my latency, because of the what was happening was the processors were getting data in at a much faster rate in the 400 megahertz version, and they were actually queuing it up at the processors. So that's one of the reasons why, with this particular architecture, you were finding that even though I was going at a faster speed, because the processor was taking longer, it was starting to queue up there, and as a result of that, the latency was going up, or the peak latency was about the same. Now, going on to my presentation, we'll follow some of the metrics that we look at in architecture analysis using performance modeling. The one you just saw was, we looked at the timing deadline, that's your latency to see if you reached it. We also looked at the resource usage, which was, what was the percentage the processor used, what was the bus usage, things like that. The other one we talked about was the processing versus the communication latency, which is the transfer time across the buses and the networks and things like that, and the effective MIPS we get. That's the efficiency. The other one, which was we looked at the model where we had two different software flows, was really the architecture of your software. So what happens if I execute, say, the DSP first and the CPU, or I run them in parallel, or I have split them up into smaller software tasks? How does the read-write request to memory change? Does it impact any of the response times? Also, what is the availability in terms of my buffer usage? In this particular case, I didn't see any data being dropped anywhere. But when I go back to the simple design, I'm going to make this buffer size to be just 3. And what I'm going to do is just increase the processing time here to be, say, 1.8. Going to run this for a little bit longer, so I'm going to run this for 20. Set this to 20. Go ahead and run it. What you're going to see now is that these 18 entered, 15 rejected. I'm sorry, 15 completed, but notice 2 were rejected. So which means that my buffer was not large enough to handle the workload coming in, as a result of which my system was not available when the incoming requests came along. So this is a major issue, because you can see here we're losing these requests, which could impact other performance downstream. So for example, if you have critical operation or safety critical operation or diagnostics, things like that, this would be a major cause of a system failure. Now, other aspects that folks can look in at performance modeling, less utilized but is still a critical issue, are things like redundancy, where you're looking at load sharing. So for example, I have a single dispatcher that sends it off to multiple cores, or say for example a TCP offload engine where everything is running on the process, and then I offload some of these functions over to an FPGA or functions to an IP block, like a TCP offload engine. How does that impact the performance? Then, of course, the other aspect that people are looking at is safety and security. So, for example, if I add another layer into my my router, which does some, say, hardware diagnostic, hardware detection to identify any faults or identify any failures or incorrect operation, how does that impact my performance? So, for example, I could have a design like this where I've got a network of different devices. Some of them have sensors, some of them actually have the electronic execution unit. And what I can do is initially run this where I've got a clean system, no faults, nothing. And this allows me to look at the architecture here, which is there were 2 processing units. The red was the first one, the blue was the second one. You see the design here, and you can see what the processing time was, and you can see the number that they exceeded the deadline and did not exceed, came below the deadline. So here, rather than having only an upper limit, you have an upper and a lower limit. Now what I can do is I can inject some faults into the system. These are already predefined faults that I'm injecting into the system. So when I run this, you'll see how the architecture changed here, and you'll also see how my response time was modified over here. So by looking at these, you can look at also how does the faults have an impact on my particular design. So that's another aspect of the architecture that I can evaluate, which is looking at how the faults behave. I'm sorry, how the system behaves in the event of a fault. Now, what are the types of exploration? See, performance analysis is all about trying to get, is this the right design? And here what you're looking at is things like, for example, is the pipeline correct? Now, could I modify the pipeline where I can add a larger buffer for each of the execution units? Or I can add a bigger pipeline to a bigger pipe to the cache? Or can I set up more cores that's reduce the clock speed of each core? Or do I have to go with an A72 ARM, or do I go with, say, a lower number of PowerPC cores? How does the set of instructions that I have on my PowerPC, how does that compare with, say, the previous generation of PowerPC? How does that behave in terms of the number of instructions that I have to execute for, say, spec mark, things like that? Also look at, for example, if I implement certain function in hardware versus software, how does that, behave in terms of, how does my system behave in terms of, being able to complete the execution of a particular frame in, say, an MPEG decoding process. The other area is looking at the software, which is, how many processors or how many cores and what should be the interconnect for the particular software. For a particular set of applications which are dedicated for this particular platform, how much should be the memory capacity, how much should be the cache, what should be the clock speed, things like that. Now, looking at comparing versus using a third-party IP block versus building something in-house, or trying to use the processor versus offloading it, allocating software tasks across multiple cores or multiple processors, looking really at where the bottleneck is in the software flow. So that way, without even making a change in your hardware, could I impact my system behavior? That way, I could eliminate, say, the bottleneck. Like, for example, I could offload the different tasks. Thus, I can get a better performance. Or maybe I don't need 14 cores. I can just be with 9 cores, things like that. Now, a quick introduction to Visual Sim. Visual Sim is the product from Miraculous Design that provides you the ability to do performance modeling, allows you to construct a model of your entire system, which can be both the hardware, software, and the network. You can look at multiple levels of abstraction, meaning that you can look at, how does it behave when I just want to get a quick overload of the entire system, which might include, say, multiple base stations, multiple IoT devices, multiple 5G handheld devices, versus looking at the internals of just a base station, trying to figure out, do I put this in an FPGA, or looking at, say, a data center and seeing if I put 8 core processors with 32 cores on each on a single board, what is the total power consumption? Are there ways we can reduce it? The Visual Sim architecture looks like this, and the key aspect of Visual Sim are the libraries that we provide. So we have a large set of these predefined libraries that you drag and drop and assemble up a system. We provide you a scripting language where you can very quickly construct up the arbitration or logic or some sort of an expression sequence that you can execute as part of your code, either as part of your behavior or as part of, say, a state machine. It gives you all the high performance simulation platform that allows you to run these models extremely fast, or run these models in a much larger period of time than you would do it otherwise. This here is the library available in Visual Sim. We have everything to build something fully custom to where you can take off-the-shelf components at an SoC level, board level, or at the network level, and you can establish your entire design. Or you can take an FPGA library component and compare what is the performance. So for example, in Visual Sim, we have complete libraries of, like, say, Zinc 7000, Zinc UltraScale Plus, Zinc UltraScale with MPSoC, or compare, say, a Zinc versus a Stratix SoCs. How does it compare for, say, a 5G application or radar application? Allows you to evaluate all of those by just dragging and dropping these libraries, as I showed you earlier, and assembling up these systems. Now, let's go over a few of the areas and try to understand how these methodologies actually play in. The first one we're going to look at is more of a flow-based architecture. So what you're looking at is an end-to-end design where I've got an ingress system and an egress system. There are multiple ingress components, and each one of them has a large number of channels. They all have the individual buffers. They get muxed in, and they have into a single set of X on X off, so their intermediate channel that then feeds into another mux that goes into a single set of egress channels. Now, the key thing here is to maintain a credit as the flow control between the between the egress and the ingress. So to ensure that the drain time is always equal to or greater than the input time. So the rate limit is really based on a weighted round robin architecture. So if I look at this design here, this is the exact same implementation of what you just saw. You can see the different traffic generators that generate the traffic associated with the different number of input channels. So we define the number of input channels as your, one second, I'm just going to move this up here, which is the ingress size over here, which is the number of channels. So I've set this to 15. So this constitutes 15, this constitutes 15, and they get fed into this ingress queues over here. These are the X on, X off for the two different flows, and that's the egress queue. Now, the actual arbitration or the scheduling of these ingress queues, the rate limitation based on weighted round robin, is defined here using our scripting language. Matter of fact, you can notice over here that we are using some special functions that are available within the scripting language, in this case, the get block status, that allows me to track what is the length of the buffer here, while at the same time also tracking what is the length of the egress buffer. So I want to check to see if it's below a threshold before I decide, okay, now I want to actually send the data over. So if it's above the threshold, I don't want to send it over, I want to hold it back. So when I go ahead and run this design, what I get to see is a couple of different things. One is I get to see the latency in terms of the actual points during the entire run. So you can see that it starts off low, but there are these spikes over here, and then it continues on. So I want to know how much of it is the spikes and how much of the latency is right down here. So I can look at the histogram plot, where you can notice most of my latency rise right here, but I got a really long tail. Matter of fact, you can see the tail extends all the way to right over here. Right here, there's a few blocks. So we're going from close to, what's it, about 0.1 microseconds, which is where most of it completes, to certain cases where it goes all the way up to 7 microseconds. I'm sorry, from 1 microsecond all the way up to about 7 microseconds. So that's kind of the range that I'm looking at. So different views allow you to take the same data and make different types of decisions. So for example, if I change the, say I change the threshold. So right now I got a threshold of 5. If I make it 3, what happens to my design? Interestingly enough, you can start seeing that the buffer occupancy is increasing over here. So it actually shoots up to 30, but then I don't see much of a change here. The reason being is that in both the cases we had it rate limited based on the buffer occupancy. Now, if I change the buffer size over here, which is this buffer over here, the queue depth, which is a parameter right over here. Oh, actually, I do change it, and there's not really much of an impact. So if I say, for example, I change the input rate and make it 60 megahertz, and try the same design, you can now see the buffer occupancy actually shoots up quite a bit. We went from about 30, it doubled to, so even though I more than doubles, I went from 20 megahertz to 60 megahertz, my buffering actually only went up from about 30 to 70. Didn't really go up 3 times, but my maximum latency, which mostly was over here, you see a larger number of spikes over here and actually went up to 9.5, so 95 microseconds. A much larger jump in terms of my response time. So using these parameters and using the different views that are provided to you, you can make decisions on, in this particular case, your scheduler or your architect or your arbitration. Another way to look at this is looking at it more at the chip level, where I've got multiple requests coming in. I come to a receiver, have a transmitter, and I've got like detailed things like free handles, addresses, thresholds, the initialization. So I can use a very detailed script like this that allows me to to define the activity between the receiver and the transmitter FIFO. So you can see there's the receiver FIFO scheduler that pops it out. So this one here is more at the signal level, not at the packet or the application level, but more at the signal level. So I can evaluate the response time, for example, looking at the power or the network latency or the MIPS, before I make a decision on my specification. So this is on a flow control. Typically, a flow control is done for things like arbitrations, throughput, looking at ingress versus egress, looking at virtual channels, interconnects, buses, networks, things like that. The other aspect is really behavior to architecture mapping. This is where I'm looking at, I've got a topology, and I want to see what happens if I say run my entire application on an ARM processor versus I move some to an hardware accelerator. Going back to Visual Sim. So this is where I've got two different behaviors. In this case, this is a phone application. So here's where I got a call versus I'm doing an MPEG video processing. Initially, I'm mapping this entire application over to a single ARM processing unit. I'm going to go ahead and run the same model. It's going to be running for about 20 milliseconds. And here's what you see in terms of the power consumption. So this is the instantaneous power. So what's the power at each instance of time? So this is running at a clock by clock. You can see a peak of about 1.4 at the instance. But then when I look at my average power, it peaks initially, but it's always below 1 watt of power. Now my goal here is I do want to keep the power below 1 watt, but my performance, which is the time it takes to complete each of those, the total number of frames, I should be able to get about 13,000 frames processed within the 20 milliseconds. And this particular design, with everything being in software, and getting a maximum of about 6,600. So now looking at some of the other statistics, I noticed that this one here is the biggest consumer of the processor. So what I'm going to do is change the setting here to say that rather than running in software, I'm going to run this alone. Everything that runs in hard software, this alone is going to be moved over to the hardware accelerator over here. Same design, no difference. The only thing is now this one alone is going to be running on this hardware accelerator. Couple of changes you're going to notice here. The first and foremost is this design over here. It was always down here at the bottom, but now you can actually see that it's starting to become active, because the rotate frame is being executed on this particular hardware accelerator. Also notice we were down here, but now you can start 1.4 was the peak. Now notice we're at like 1.95. This one now, this is the bigger issue, is that we're at like 1.5 watts of power, which is earlier on we were at 1, now we got up to 1.5 watts of power. But our performance peaked to about 14,100. So we got our performance, but didn't get our power consumption. Now, same design, and I'm not going to go into too much detail because it's related to power and we're only going to focus on the performance. But what I'm going to do is introduce a power management element, which is if it stays in standby for a certain period of time, I'm going to move over to the idle state. So here what I'm going to do is same design. I'm going to rerun the whole thing, but now I've got this one in hardware acceleration, and now I've added a power, I turned on the power management for this for the hardware accelerator. That's the only changes I'm making. So if you notice, I'm making incremental changes and seeing how the system behaves as a result of being in these incremental states. Couple of things you notice. One thing is, as soon as it finishes the task, immediately drops to an idle state, which is almost 0. Power is looking pretty good. It's below the 1 watt of power. And the performance actually drops off a little bit, but not significantly. That's because I haven't set a transition time for the particular design. Now, if I set a transition time looking at, the time that it takes to reload the caches and move things from memory, you might see an additional loss in the performance. But I wouldn't be very far off. It might be about 10, 11% here. The key thing is this aspect here. Now, same model, but I'm going to run this again. And here what I'm going to do is set this to have an additional transition time related to the migrating from an idle state back to an active state. The same architecture. Now I'm going to study the impact of the transitions associated with the behavior of the particular design. Now I'm looking at this and notice that I'm below the 1 megawatts and performance is not impacted all that much. So now I know that I can actually achieve my performance based on just offloading this one particular rotate frame over to the hardware accelerator, keeping everything else in software, but just that one element. So I can use this for trying to figure out how I can partition my application or my firmware across my particular design. So what we were looking at is looking at it as 3 separate entities: the architecture, which is the hardware software platform; the behavior, which is what is the application running on my system. And notice I'm using the word application or behavior, not software, because in this case, remember, we moved this over to a hardware accelerator. And the third one is your input. In this case, the input happened to be the power consumption of my particular design. Combining all of it, I could get a variety of statistics of my particular design. The third aspect here is looking at software. Now, what we're looking at is aspects such as, I've got an operating system with a scheduler, I've got the real-time runtime environment, and I've got the software tasks running on top of it. So now my question is, what happens if I change, say, the clock speed, or what happens if I change the sequence, the task offset time? How does that impact my performance? So now I'm going to go back here and look at a design we just looked at a little while ago. So again, as I mentioned, we have a network. A network doesn't mean an Ethernet network or an IT network. It could, of course, mean that, but it could be a network on chip. It could be like a token ring that is connected to multiple processors or multiple cores. In this particular case, multiple sensors are connected, and this one here has the ECU hardware, the RTOS, the runtime environment, the runnables. Runnables meaning the actual software application. So here, when I run this, I can see, for example, what was the processing time and what was the power consumption. Now, what I can do here is I can change the clock speed. I can say speed megahertz to go to say, say 4 microseconds. And I can change this here. Okay, so I got these states that I'm changing them into. Same design. We'll see what happens now. Notice the key thing is that a lot of tasks are completing. So you see the live indications right here on the deadline. A lot more are finishing before the minimum deadline. So the minimum deadline is required so that the diagnostics or tasks do not arrive too far ahead at the processor, which means you're just going to wait idling in the processor as opposed to arriving exactly at the time that it's expected to. Why is this important? If I'm running on a GPS, I might want the data at a particular time point in my design. If for example, I'm braking, I don't want to use an earlier data, I want to add the current data. So it's important that it's not just a maximum deadline, but also a minimum deadline is incorporated. So very quickly, you can see if I change some of the clock speeds or I change certain other attributes of my design, like for example, I could change the task table, which means, okay, here we go. I can set the priority of these different tasks, and I can set the time at which the offset time at which they're triggered, and then I can see how this impacts. So these are different runtime environments, so they have their own schedule. And these are the offsets for each one of them within those schedules. So I can, for example, see what happens to my design if I change the sequence of these or change these preconditions for each one of these tasks. How does that impact my particular design? This is a very common exploration that is done by folks that are evaluating different RTOS conditions. So for example, if I change the number of preconditions or I set some of these to be interrupt driven, some of them to be event driven, some of them to be on a schedule, how does that impact the performance of my system? So allows me to have those settings to evaluate the quality of my operating system. So if I change the different timing schedules or different weightages or different attributes in my operating system, how does that impact my performance? So allows you to set the different parameters or different attributes of an operating system on different hardware platforms. How do they behave? How do they impact the system? The last aspect I'm going to be looking at is looking at it at a cycle accurate level. What that means is rather than looking at it at a packet or a message level or looking at the full system or the overall design, looking at a specific subsystem. So in this particular case, I'm going to be looking at a portion of the system, which is I've got 4 different resources in my system that goes through an AXI bus to a memory controller. Each one of these has a different address, different clock rate, different internal buses, and different burst length, and they also have different priorities. I have the settings for the request threshold, the read-write thresholds, and the throttling on the master and slave side. And then of course I have my memory controller, which has all the timing requirements for, like, say, a DDR2, DDR3, DDR4, or even up to a DDR5. It actually extracts the row column bank information from the address that's being fed in through the request that's coming in from these different hardware devices. So allows me to set it more at the address or more at the cycle accurate level where I can see what happens clock by clock. So in this particular case, when I run the simulation, What I'm going to see here is I see what happens, on my bidirectional bus, my writes, my reads. You can see which bank it's addressing. Here, for example, I can see the memory controller, how many read IOs, how many write IOs, what was the total megabytes per second I'm getting out of the system. Also on my AXI bus, I can see the megabytes per second. I can, for the writes, I can also see I can see the megabytes per second and the IOs per second for the reads. Also look at I can look at the overall statistics as well for for the design. So for example, at 25 microseconds, I can see that my max value was about 2003, and my mean value was 1776, and my minimum was 45. So allows me to be able to evaluate different attributes of my particular design. So what we were looking at is using our statistics block, and this being fed in, it was capturing the latency time in number of cycles. So what you were looking at is the cycle count that it took to start from the traffic, go across the tube level buses, and go into the memory, and then come all the way back. And you can see how many cycles that took to complete. So for example, I can change, say, the memory device. So I can say use a Micron DDR4 2600, or use say a Micron 1333 megahertz DDR4. How does the performance change? Or for example, I can set the priority of some of these at a different level and see how that impacts my particular design. So allows me at a very detailed level to be able to describe what happens to my particular architecture. Allows me to evaluate different scenarios, different topologies, different different settings in terms of offsets or addresses or partitioning of my memory. Allows me to do all of those kind of allocations also. So why do this performance modeling as a wrap up? The reason to do performance modeling is really looking at two different concepts. The first one is where you do a traditional approach of doing like an Excel spreadsheet or doing some software C code analysis to come up with trying to determine where my bottleneck is. The biggest thing is spending less time upfront for constructing the model, more time to doing the analysis, and also being able to do the analysis much earlier in the design cycle. So you're not actually doing the analysis while the development is happening, but doing the analysis before the development is happening. So that way, the idea is that your implementation takes much shorter. The biggest reason being that you're identifying the bottlenecks, your requirements, your specifications much earlier in the cycle. So that way, when you're doing a development, you're not finding the errors at that point and fixing it. Of course, you'll find implementation related errors, but not architecture related errors. So you're being able to identify some of those much earlier in the design process. So obviously this increases in terms of your ability to deliver on schedule or deliver at a much faster rate than you would otherwise be doing. With this, I would like to wrap up my presentation. Now I'm open to answering any questions that you might have. You can go ahead and type your questions in the chat window, which is on the panel to the right of you, and I'll be happy to answer those questions.